Today's lesson will focus on finding the exact values of trig functions. We'll go ahead and use the unit circle approach to define and derive them, as well as find the exact values of the 6 trig functions at the key angles in a unit circle. And finally, we will find the reference angles with respect to a given rotation, which will help us in defining those exact values. Shown here, this image represents a unit circle. We have all the degrees listed, and we have the radian measures related to those degrees. But now we have these other items. These are exact values for our key angles in our unit circle, and that's what we'll be looking at today. Let's go ahead and start by reviewing our trig functions. Our 6 basic trig functions are sine, cosine, tangent, cosecant, secant, and cotangent. If you learned SOHCAHTOA, this might help you to remember that sine, for example, so is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent, is opposite over adjacent. The reciprocal functions then are easy to remember because those are just reciprocals of our 3 main trig functions. So take a minute and study this if you need to, but this is how we will derive our exact values. Let's go ahead and start by proving in a unit circle that the sine of theta is y, the cosine of theta is x, and the tangent of theta is y over x. This is very easy to prove. Here we have a unit circle. If we draw an angle theta, and I connect down to the x-axis so that we can see the right triangle, then I can define the distance along the base here as x, some distance x. The vertical distance is then y, some distance y. So the exact value at this point on the circumference is just x comma y. Now notice this is a unit circle, so our radius is 1. Well, let's look at sine. We said sine was opposite over hypotenuse. The opposite is y, and the hypotenuse in this case is 1, which simplifies to y. Let's look at cosine. Cosine, we said, was adjacent, which is an x value here, over our hypotenuse, which is 1. That simplifies to x. And then tangent is opposite over adjacent, y over x. So therefore, in a unit circle, sine theta is y, cosine theta is x, and tangent theta will be y over x. Now let's look at our reciprocal functions. All we have to do is take the reciprocal. Cosecant is a reciprocal function to sine, so that's going to be 1 over y, secant to cosine, 1 over x, and cotangent to tangent, x over y. So we will be using this understanding quite a bit as we move forward over the next few weeks. Let's go ahead now and define those exact values for x and y. So what is x and y at certain key angles? Let's start with a 45-degree angle. Here we have a square, a perfect square. So every angle is 90 degrees. If I were to split the square into 2 right triangles, then I would have a 45-degree measure here, which looks like this on the unit circle. Notice that where I'm splitting this hypotenuse has a measure of 1 because this is a unit circle and the radius is 1. So what we need to do then is define what our x value is and define what the y value is so we know what the exact value is here at 45 degrees. Well, what we can do is apply the Pythagorean theorem, and we can say that the distance x here is not a squared yet, it is just a, and if this distance is some value a, then because it's a square, this value has to be a as well. Applying the Pythagorean theorem, then we would get a squared plus a squared equals 1 squared, which simplifies into 2a squared equals 1. If we divide both sides by 2, we end up with a squared equals 1/2. To solve for a, we then need to take the square root of both sides, which gives us the square root of 1 over the square root of 2. When we are working with trig functions, we never want to leave a radical in the denominator. That's not a simplified version. In order to eliminate the radical from the denominator, it's very simple. All we have to do is multiply numerator and denominator by that radical. If we do that, radical 1 times radical 2 gives us radical 2. Square root 2 times square root 2 is just 2. And now we've eliminated the radical from the denominator, so we have simplified this to be root 2 over 2. Now we know what these values are. They're both going to be root 2 over 2. If you have your unit circle handy that you printed out prior to this lesson, go ahead and write in at the 45-degree rotation, root 2 over 2, comma root 2 over 2. That's the exact value for x and y. So we know that cosine then is root 2 over 2, and the sine of 45 degrees is also root 2 over 2. Let's go ahead and do the same thing, but with a 30 and a 60-degree angle. We can derive that by taking an equilateral triangle where all angles are 60 and all sides are the same measure. Again, because this is a unit circle, we know that each of the sides would be 1. So this side is 1, this side is 1, and the entire base is 1. But if we cut this in half to create two right triangles, we know then that each of these will actually be 1/2. So in our unit circle, we can define the radius as 1. We can define our y length as 1/2. But what about our x value here? What is x going to equal? Again, we can use Pythagorean theorem to determine this value here. And we'll go ahead and just call this b. So if we look at this as a right triangle, we can do b squared plus 1/2 squared equals 1 squared. And that simplifies to b squared plus 1/4 equals 1. If we subtract 1/4 from both sides, then b squared equals 3/4. And finally, taking the square root, a very faint square root, we end up with b equals square root 3 over square root 4, which is just square root 3 over 2. So this value here is square root 3 over 2. We can transfer this information to this diagram as well. If you can picture the full equilateral triangle coming down here, we know that this distance is our 1/2, and this vertical distance now is our root 3 over 2. So quickly now we have defined exact values for both a 30-degree and a 60-degree angle. So again, on your unit circle, if you have your blank one with you, you would fill in root 3 over 2 comma 1/2 for our 30-degree rotation, and you would fill in 1/2 comma root 3 over 2 for our 60-degree location. If I were to ask you what is the cosine of 30 degrees, you would easily be able to tell me that it was root 3 over 2. Let's go ahead now and look at reference angles. These are really important now that you have defined the key angles, or I should say the key exact values for these key angles in this first quadrant. So what happens if we have an angle in another quadrant, say 150 degrees? Let's draw that angle. Here we have the angle 150 degrees. So this line here is our terminal side. And if you'll notice the definition of a reference angle, it is the acute angle formed by the terminal side of theta and the x-axis. Well, this is our terminal side in purple, and the acute angle formed between that and our x-axis would be in between these two purple lines right in here. So this theta here is our reference angle, and that distance would be 30 degrees. 150 plus 30 gives us the full 180. So when we are finding exact values, we can look at the 30-degree exact value that we had here to define what the exact value would be here at 30 degrees. So if we notice that this 30-degree angle is the same as this 30-degree angle, we define the exact value at 30 degrees to be root 3 over 2 comma 1/2. So since 150-degree rotation lands us on a reference angle of 30 degrees, we have the same exact value, except for that because we're in quadrant 2, our x is now negative root 3 over 2. Go ahead and pause the video and see if you can define the reference angle for each of these three angles. For B, 240 degrees, drawn in green here, the reference angle is this distance back to the x-axis. Think of it as it's always going to be the shortest distance between the terminal side here in green and the closest x-axis. And we know that reference angle is 60 degrees. For C, 5 pi over 3, the reference angle you should have gotten was 60 degrees, or because it's in radian measure, we would be more appropriate to leave it in radian measure, pi over 3. These are actually easier because all you have to do is look at the denominator and think of the denominator, pi over 3. What angle does that represent? That represents a 60-degree angle. I have drawn in the rotation, 5 pi over 3, to here. The distance from this terminal side to the closest x-axis is 60 degrees, or pi over 3. Using the same logic we did in C, if you look at D, because the denominator is 4, the reference angle would have to be pi over 4, which you know as 45 degrees. If we were in fact to rotate around, we would end up with 8 pi over 4 here back at the origin, and then another pi over 4 would take us right up here to this terminal side, and this distance in here is just pi over 4, or 45 degrees. So remember that these reference angles are to help you define the exact values for a given rotation. Now what I want you to do is take out your blank unit circle, which hopefully has the exact values filled out for 30, 45, and 60, and then I want you to go ahead and see if you can fill out the rest of these exact values. I've filled out a couple just to give you a hint in case you get lost. Let's go ahead and examine those. If we rotate to here, this is 3 pi over 4. This first distance is 1 pi over 4, 2 pi over 4, and then 3 pi over 4. We know that the reference angle for this right here is just pi over 4, or 45 degrees. So if you look at your blank unit circle, you would see that this is root 2 over 2, and this is root 2 over 2 at 45 degrees, or pi over 4. Therefore, this has to be root 2 over 2, root 2 over 2. However, notice that along the x-axis, we are in quadrant 2, x would be negative. Same goes for this last one here. Because we're down in quadrant 4, y is negative. But notice that this is a rotation of 300 degrees, or 5 pi over 3, which leaves a reference angle of pi over 3. So you can look here on your blank unit circle to see that the exact values would match these with the exception of the negative. So go ahead and pause the video and see how you do. At the end of this week, there is a completed unit circle for you to check your answers. Okay, to finish off this lesson, you might be asking yourself, so what are we going to be doing with these exact values? Well, we're going to be finding different trig functions. So let's go ahead and get started. I have up here 5 examples to show you, and then you'll try some on your own when you're doing the practice. So let's find the secant of 90 degrees. Think about how you might do that. 90 degrees we know is right here, and we know the exact value there is 0, 1. So how can you find the secant? Remember that secant is the reciprocal of the cosine. So what is the cosine at 90 degrees? Well, the cosine is 0. So the secant would have to be the reciprocal of 0 over 1, which is 1 over 0, which doesn't exist. So we would say that the trig function's exact value here is undefined. Let's try the tangent of 2 pi over 3. Well, the first thing is to figure out where that is. Well, here's 1 pi over 3. Here's 2 pi over 3 right here. Well, what is the tangent? Remember, the tangent is opposite over adjacent, or y over x, or sine of theta over cosine of theta. Well, we know the sine is going to be root 3 over 2, and we know that the cosine here, and be careful of the sign, it's negative 1/2. Well, obviously we can't leave an answer like this. This isn't very simplified. But if we have common denominators, those can cancel, and we're left with an exact value here of a negative root 3 over 1, or just negative root 3. Now it's your turn. Hopefully you're getting the hang of this. Try the next three on your own. Hopefully you identified that the cosecant is the reciprocal of the sine. And the sine at pi over 4, you'll notice, is our y value, which is root 2 over 2. So it's going to be 1 over root 2 over 2, which we can't leave like that either. So that's the same thing as 1. Instead of divided by root 2 over 2, we would multiply it by the reciprocal, 2 over root 2. Which gives us 2 over root 2, and as you know, we cannot have a radical in the denominator. So we would multiply both the numerator and the denominator by root 2, and that would leave us with 2 root 2 over 2. Square root 2 times square root 2, remember, is just 2. However, 2 and 2 can cancel, and we'll be left with a final answer here of just root 2. Seems like a lot of work just to get the root 2. Part of being proficient with trigonometry is being proficient with simplifying and reducing these fractions. So the more you practice, the better you'll get. Let's move on to cosine of 210. If I move around the circle and I find 210 degrees, all I have to do is pull off the x-coordinate to find the cosine. Notice though it's negative, negative root 3 over 2. And finally, let's go ahead and look at the tangent of 300 degrees. The tangent of 300 degrees is going to be here. And remember that the tangent is y over x. So again, we have negative root 3 over 2 divided by 1/2. Our 2's can cancel, and our final answer is negative root 3. Hopefully you've been noticing how important it is to have a filled out unit circle with degrees, radians, and exact values. Again, if you haven't filled out your blank unit circle, go ahead and try to fill that out on your own. It's very helpful to understand the information by doing it on your own before you just copy one that's already filled out. Also, you'll really want to try to memorize these values as much as possible so that it makes performing these exercises quicker and seamless. And that concludes our lesson for today on finding exact values of trig functions. Hopefully now you understand how to define and derive these functions, as well as how to get the exact values of the 6 trig functions at all the key angles in a unit circle, as well as use the reference angle to help you identify.